Hello everyone, my name is Aiman. Today representing Group 2, I am excited to introduce our project on high frequency NPN BJT base layer engineering. In the modern semiconductor manufacturing, creating a fast, efficient, high frequency bipolar junction transistor or BJT is absolutely crucial for RF and communication application. The heart of NPN transistor performance lies in its P-type base layer. To engineering this layer with the assembly precision, we are utilizing boron 11 ion implementation into a silicon wafer, often through a protective silicon dioxide screening layer, to precisely control the dopant distribution without damaging the underlying crystal lattice. This brings us to our core engineering challenge and project requirement. For high frequency BJT to function optimally, the base transit time of electrons needs to be minimized. This means we need very tight uniform box profile for our dopant. Specifically, our target window for this base layer is between 100 nanometer and 250 nanometer deep. If the layer is too shallow or too deep, the frequency response drops significantly within this zone. We are aiming for a uniform target doping concentration of 4 times 10 to the power 17 atoms, allowing a strict uniform tolerance of just plus or minus 10%. To achieve this perfectly flat box-like profile, we cannot just use a single ion implementation step. We have to simulate and design a multi-energy implant strategy. However, we are bound by our high constraint. Our ion implementer has maximum stable acceleration of potential of 80 kilo electron volt and minimum stable acceleration potential of 10 kilo electron volt.
Now I will walk you through the physics and design of our implantation recipe. Our primary challenge for this NPN BGT base layer was boron's high rate of electronic straggle. We needed to achieve a perfectly flat box profile between 100 and 250 nanometers, but doing this with a single implant is physically impossible without violating the 80 keV tool limit. Therefore, we engineered a four-step chain implantation recipe. We selected precise acceleration energies at 25, 40, 50, and 61 keV. By capping our absolute maximum energy at 61 keV, we ensure that complete tool stability and zero risk of high voltage arcing in the accelerator column. You'll notice that our doses are heavily weighted. We applied the largest dose, which is 4.6668 times 10 to the power of 12 ions per square centimeter at the 61 keV step. This effectively anchors the deep 250 nanometer boundary, while the lower energy and lower dose implants fill in the shallow regions to maintain the plus minus 10% uniformity. The trim simulation outputs a normalized depth distribution for each step, represented here as y-axis. To translate this raw data into the actual dopant concentration, we scale each y-axis curve by our specific operational dose. Since these four discrete implants do not physically interact to alter each other's stopping ranges, the final post-implantation doping profile, C final X, is a direct linear superposition of the four individual Gaussian distributions. By calculating the sum of these scaled profiles, we deliberately overlap their straggle tails. This mathematical superposition is exactly what smooths out the internal peaks and valleys. It allows us to hit our target concentration completely flat across the active window, while mathematically guaranteeing that the boron tail drops safely below the punch-through leakage limit at 350 nanometers.
Well, like before we start to discuss our process as a process integrations engineers, I would like to say we are choosing the four-step ion implantation recipe. However, by using the four-step ion implantations recipe, it has several advantages and disadvantages. Like firstly, undeniably, the process time for four-step will be longer compared to three-step, but it will reduce the leakage currents and also the depth coverage, which is have a better control and allowing a more uniform on 100 nanometers to 250 nanometer scales. On the other hand, by using the analysis in MATLAB, we also know that the concentration distributions on four-step ion implantation will be more constant compared to three-step. As you can see, like the graph, the blue color graph at here, the four-step will be more evenly the concentrations compared to three-step. And on the other hand, like the process control for four-step will be much more better than three-step, because in four-step, like the weightage we can give on four process, while on three-step we can only control three process in this case. Therefore, in our case, we are going to choose the four-step ion implantations recipes. Like since our objective is to have very good controls and also very uniform concentrations in between 100 nanometer to 250 nanometers. We are going to use 4 energy, which is 25 keVs, where the projected range around 112. And the second one, we are going to use 40 keVs, where the projection range will be around 160, and also 50 keVs, the projection range will be 182. And finally, we are going to use 61 keVs, where the projection range is around 207. Well, we are going to use this type of energies because we need to cover the projection range from 100 until 250 nanometers in order to create a uniform concentrations in this area.
Thank you, Kaheng. So my name is Nur Ilyani and I would like to focus on the result of 24 kilo voltage and how its low projected range effect on the 100 nanometer. The 25 KE voltage implant has the lowest implantation energy among the 4 implantation steps. Because of this low energy, the boron ion have a low projected range, meaning they cannot travel very far into the silicon wafer. Instead, they stop close to the surface after passing through the silicon dioxide layer. This shallow penetration is important because our target box profile start at 100 nanometers. The 24 kilo voltage implant is specifically chosen to place the highest boron concentration near this depth, forming the upper boundary of this base region. In other words, it ensures the shallow region is stopped accurately without implanting too deeply into the silicon. However, because of its low projected range, the 25 KE voltage implant alone cannot reach the deeper region of 200 to 250 nanometers. If only 24 KE voltage were used, the dopant concentration would decrease rapidly with depth, resulting in a non-uniform profile that does not meet the design requirement. Therefore, the 25 KE voltage implantation work together with the higher implantation energies, while 25 KE voltage established the shallow 100 nanometer region. The 40, 50, and 61 kilo voltage implants extend the dopant distribution deeper into the silicon. The combination of these implantation energies produce a more uniform box-shaped dopant profile across the target depth.
Hello everyone, my name is Zhang Yingzhou and my metric number is A198950. Now let us look at the middle and deep parts of our chip layer. To fill the middle space, we used 2 energies, 40 keV and 50 keV. They work together like a bridge. They overlap each other. Our team used a computer code to calculate this. They make the total line very smooth and flat in the middle. But the real problem is that the deepest part, the 61 keV step. Boron is a very light atom. When it has a high energy, it flies everywhere inside the silicon. This is because of the large electronic struggle. If we use too much energy, the boron will go too deep, past 350 millimeters. This will cause back leakage problems. To solve this, our design limits the energy to 61 keV, but we give it the highest dose, 4.66. This strong dose push the deep wall to 250 millimeters. It makes the whole box shape very beautiful and uniform. Look at our final screen. Our extra doping is between 3.62 and 4.08. This is the perfect path for the uniformity. At the same time, our leakage at the 350 millimeters is only 2. This prevents the base collector punch through leakage. We don't need high temporary furnace step. This is safety below the limit line. Now, Li Junhan will conclude our work. Thank you for your listening.
To conclude, our project studied the ion implantation process in semiconductor manufacturing using SRM TRM simulations. By comparing boron 11 and arsenic 75, we found clear difference in penetration depths, lateral spreading, and lattice damage. For our final design, we focused on boron 11 implantation to form the base layer of high-frequency NPN BJT. By using a 4-step multi-energy implantation recipe, the dopants were spread across different steps instead of forming only one peak. As a result, we achieve more box-shaped and the uniform dopants profile within a target depth range of 100 to 250 nanometers. The profile was close to the required doping concentration. However, this method also had a trade-off. More implantation steps can increase processing time, complexity, and cost. Overall, this project showed that optimizing implantation energy and the dose is important to achieve a controlled and reliable semiconductor doping profile.